6,000 years ago, and the cradle of civilization between the Tigris and Euphrates rivers. Sumerian astronomers carved astronomical observations into clay tablets that would remain buried for millennia. When archaeologists finally deciphered these ancient texts in the 19th and 20th centuries, they discovered something that challenged everything we thought we knew about the progression of human knowledge. These Bronze Age scribes had recorded detailed information about planets in our solar system that modern science wouldn't officially discover until the late 1700s and beyond. The implications of this discovery reach far beyond simple historical curiosity. We're confronting evidence that suggests our ancestors possessed astronomical knowledge that, according to conventional timelines, should have been impossible for them to obtain. With no telescopes, no advanced mathematics as we understand them, and no apparent means of viewing distant celestial bodies, the Sumerians somehow documented planetary characteristics that match modern observations with startling accuracy. Consider the planet Uranus, officially discovered by William Herschel in 1781. This distant world orbits our Sun at an average distance of 1.8 billion miles, appearing as nothing more than a faint speck even through modern telescopes. Yet Sumerian texts from 4000 BC contain references to a green star in the outer reaches of the heavens, describing orbital characteristics that align precisely with Uranus's actual path through space. They called it Enuma Anu, meaning the light of the heavens, and attributed to it qualities that modern astronomy has confirmed through centuries of observation. Neptune presents an even more perplexing case. This ice giant, located to 0.8 billion miles from Earth, wasn't officially discovered until 1846, and then only through mathematical calculations predicting gravitational anomalies in Uranus's orbit. The planet is completely invisible to the naked eye, requiring powerful telescopes to observe, yet Sumerian astronomical texts reference Humba, a distant blue world associated with water and storms, located in the far outer realm of their cosmological maps. Recent analysis of these descriptions reveals correlations with Neptune's actual characteristics that extend beyond statistical probability. But perhaps most disturbing of all is the Sumerian documentation of what they called the 12th planet, a massive celestial body following a highly elliptical orbit that brings it into the inner solar system approximately every 3,600 years. Modern astronomers have been searching for exactly such an object since 2016, when Caltech researchers Mike Brown and Konstantin Batygin published evidence suggesting the existence of Planet 9, a super-Earth located in the outer reaches of our solar system, following an elongated orbit that matches, with remarkable precision, the ancient Sumerian descriptions. Dr. Zechariah Sitchin, who spent decades translating Sumerian texts, argued that these ancient astronomers possessed knowledge that could only have been obtained through direct observation or information and transfer from a more advanced source. While mainstream archaeology initially dismissed his translations as speculative, subsequent discoveries have forced a reconsideration of what early civilizations might have known about our cosmic neighborhood. The Enuma Anu, the Sumerian creation epic, contains a sophisticated model of planetary formation that predates modern cosmological theories by thousands of years. It describes the solar system as originally containing additional planets, explains the formation of the asteroid belt through planetary collision, and accounts for the unusual characteristics of several worlds that would be officially discovered until the space age. NASA's Kepler space telescope, launched in 2009, has confirmed that planetary systems often contain more worlds than initially visible, that planetary collisions shape solar system architecture, and that distant planets can follow highly elliptical orbits that make them virtually indetectable for long periods. These findings align with Sumerian cosmology in ways that challenge our understanding of how ancient knowledge systems developed. Tonight, we're examining the evidence that suggests our earliest civilizations possessed astronomical knowledge that shouldn't have been possible given the technological limitations of their era. We'll explore specific planetary descriptions found in Sumerian texts, compare them with modern astronomical data, and investigate the implications of these correlations for our understanding of human history and the development of scientific knowledge. We'll uncover how the Sumerians described the composition of distant worlds, documented orbital mechanics with mathematical precision, and created star maps that remain accurate today. We'll examine the archaeological evidence supporting these claims, investigate alternative explanations for their knowledge, and consider what these discoveries mean for our assumptions about the linear progression of human understanding. If you're fascinated by the intersection of ancient wisdom and modern discovery, subscribe and hit the thumbs up button. And here is a question that might change how you think about human history. What if our ancestors weren't primitive observers of the night sky, but sophisticated astronomers working with information sources we're only beginning to understand? Share your thoughts in the comments below. I'll pin the most insightful response. The journey we're about to undertake will challenge fundamental assumptions about the development of human knowledge and force us to reconsider the capabilities of our earliest civilizations. From the libraries of ancient Babylon to the laboratories of modern space agencies, we're tracing a thread of astronomical understanding that spans millennia and suggests possibilities that mainstream academia is only now beginning to acknowledge. Now let us begin our investigation into one of the most compelling mysteries in the intersection of archaeology and astronomy. Ancient texts. The story begins in 1849, when British archaeologist Austen Henry Layard uncovered the library of Ashurbanipal in the ruins of Nineveh. Among the 30,000 cuneiform tablets discovered in this ancient repository were astronomical texts that would fundamentally challenge our understanding of early human knowledge. These weren't simple recordings of lunar phases or seasonal observations. They were sophisticated astronomical treatises containing information about celestial bodies that shouldn't have been visible to Bronze Age observers. The Mul.Apin tablets, dating to approximately 1000 BC but containing astronomical knowledge that Assyrian scribes claimed to have inherited from much earlier Sumerian sources, present the most detailed ancient astronomical compendium ever discovered. These texts catalog over 60 celestial bodies, organize them into 3 distinct ways or celestial paths, and provide mathematical calculations for planetary movements that demonstrate an understanding of orbital mechanics thousands of years before Kepler formulated his laws of planetary motion. What makes these tablets extraordinary isn't their existence. Ancient civilizations were known to observe the heavens, but rather their content. The Mul.Apin texts describe celestial bodies using terminology and characteristics that aligned with planets unknown to mainstream science until the telescope age. They reference wandering stars in the outer darkness, worlds associated with specific colors and atmospheric phenomena, and orbital periods that match planets discovered only in the last 3 centuries. Professor Hermann Hunger of the University of Vienna, who spent decades studying these astronomical texts, noted that the mathematical precision contained within them suggests access to observation technologies or calculation methods that far exceeded what archaeological evidence indicates was available to ancient Mesopotamian cultures. The tablets contain stellar coordinates, planetary conjunction predictions, and eclipse calculations that remain accurate when tested against modern astronomical software. The Enuma Anu Enlil, a massive collection of 70 tablets devoted to celestial omens and astronomical observations, provides even more detailed planetary information, dating to the 7th century BC but claiming to preserve knowledge from the dawn of Sumerian civilization. These texts describe a solar system containing planets beyond those visible to the naked eye. They reference distant worlds characterized by specific atmospheric compositions, magnetic field properties, and orbital eccentricities that correlate with modern measurements of outer solar system planets. Tablet 63 of the Enuma Anu Enlil contains particularly intriguing passages describing what the scribes called the outer wanderers as celestial bodies that appear and disappear from view, according to vast cyclical patterns. The text describes these objects using terminology that, when translated into modern astronomical language, corresponds to the highly elliptical orbits characteristic of trans-Neptunian objects and distant dwarf planets. The mathematical relationships described in these passages align with gravitational dynamics that weren't formally understood until Newton's work in the 17th century. The Venus tablet of Emisaduka, one of the oldest surviving astronomical documents, demonstrates the sophistication of early Mesopotamian astronomical observation. This text, dating to 1650 BC, records the synodic period of Venus with an accuracy that rivals modern measurements. But beyond this well-documented achievement, the tablet contains references to planetary relationships and celestial mechanics that suggest knowledge of gravitational interactions between distant worlds, concepts that would be formally developed until the space age. Dr. David Brown of the University of Oxford, who has extensively studied Mesopotamian astronomical texts, argues that these documents represent the culmination of thousands of years of systematic observation and mathematical development. His analysis reveals that Sumerian astronomers employed sophisticated predictive models for planetary motion, understood the concept of celestial sphere rotation, and possessed mathematical tools for calculating long-term orbital mechanics that weren't rediscovered in Europe until the Renaissance. The astronomical content of these texts extends beyond simple planetary observations to encompass a comprehensive cosmological model. The Sumerians described a universe containing multiple invisible celestial bodies, understood that planets followed elliptical rather than circular orbits, and possessed knowledge of magnetic field interactions between worlds. They described atmospheric phenomena on distant planets, knew the relative compositions of planetary atmospheres, and understood that certain worlds possessed multiple moons with complex orbital relationships. Archaeological evidence suggests these texts weren't produced by a single generation of astronomers but represent the accumulated knowledge of a sophisticated observational tradition spanning millennia. The consistency of astronomical information across different sites, time periods, and cultural contexts indicates a formal system for preserving and transmitting complex mathematical and observational knowledge across generations. The translations of these texts, first undertaken by scholars like George Smith and Hormuzd Rassam in the 19th century, initially focused on historical and mythological content. It wasn't until the 20th century, when archaeoastronomers began applying modern astronomical knowledge to ancient texts, that the sophisticated scientific content became apparent. Scholars like Otto Neugebauer and Abraham Sachs demonstrated that these tablets contain mathematical astronomy of remarkable sophistication, employing computational methods that wouldn't be rediscovered until the medieval Islamic period. Recent advances in computational archaeology have enabled even more precise analysis of these ancient astronomical texts. Computer modeling of the planetary positions described in Sumerian tablets reveals that their observations match actual celestial mechanics with accuracy levels that exceed what should have been possible through naked eye observation alone. The data suggests either access to observational technologies now preserved in the archaeological record or information sources that remain unexplained by conventional historical models. The preservation of these texts themselves presents additional mysteries. The astronomical tablets were clearly valued by ancient scribes, copied and recopied across millennia, and preserved in multiple locations across Mesopotamia. This suggests that their astronomical content was considered foundational knowledge worth preserving across cultural and political changes. The care taken in maintaining astronomical accuracy across these copies indicates that the scribes understood they were preserving scientific information rather than mythological or religious content. Modern analysis of the mathematical techniques employed in these texts reveals computational sophistication that challenges assumptions about the development of mathematical knowledge. The tablets employ base 60 arithmetic, positional notation systems, and algebraic methods for solving complex astronomical problems. They demonstrate understanding of trigonometric relationships, geometric principles for calculating celestial distances, and mathematical modeling techniques for predicting long-term planetary behavior. These ancient texts represent the foundation of what would become humanity's most precise science, astronomy. They demonstrate that our earliest civilizations possessed not just observational capabilities but mathematical and theoretical frameworks for understanding cosmic mechanics that wouldn't be matched until the scientific revolution. The accuracy and sophistication of their content suggest possibilities for ancient knowledge acquisition that continue to challenge our understanding of human intellectual development. Hidden giants. Among the most compelling evidence for advanced Sumerian astronomical knowledge lies in their documentation of planets that remained hidden from modern science until the invention of powerful telescopes. The ancient texts describe distant worlds with characteristics so specific and accurate that their correspondence with actual planetary properties defies conventional explanations for how Bronze Age civilizations could have acquired such knowledge. Uranus, the seventh planet from our Sun, orbits at an average distance of 1.8 billion miles from Earth. Even at its brightest, this ice giant appears as nothing more than a barely perceptible speck in Earth's sky, requiring significant telescopic magnification for detailed observation. The planet wasn't officially discovered by modern astronomy until March 13, 1781, when William Herschel identified it as a new celestial body while conducting systematic observations from Bath, England. Yet Sumerian astronomical texts from the 3rd millennium BC contain detailed references to what they called Enuma Anu, a greenish celestial wanderer located in the outer reaches of the heavens. The Sumerian description of Enuma Anu includes details that align precisely with modern knowledge of Uranus. They described it as possessing a sideways rolling motion, an observation that corresponds to Uranus's unique characteristic of rotating on its side, with its polar axis tilted 98 degrees relative to its orbital plane. This extreme axial tilt, which causes Uranus to essentially roll along its orbital path rather than spinning upright like other planets, wasn't confirmed by modern astronomy until Voyager 2's flyby in 1986. The Sumerians somehow documented this distinctive rotational behavior over 4,000 years before space-age technology made direct observation possible. Even more remarkably, Sumerian texts attributed specific atmospheric qualities to Enuma Anu that match modern spectroscopic analysis of Uranus's composition. They described it as surrounded by rings of ice and stone and characterized its atmosphere as containing the breath of the deep cold. Modern astronomy has confirmed that Uranus possesses a ring system composed primarily of ice particles and rock fragments, and its atmosphere consists largely of hydrogen and helium with significant methane content that gives the planet its distinctive blue-green coloration. The temperatures in Uranus's atmosphere reach -370 degrees Fahrenheit, making it one of the coldest planetary environments in our solar system. Neptune presents an even more extraordinary case of apparent ancient knowledge. This distant ice giant, located to 0.8 billion miles from Earth, is completely invisible to naked eye observation and wasn't discovered by modern science until September 23, 1846. The planet's discovery came through mathematical predictions rather than direct observation. Urbain Le Verrier and John Couch Adams independently calculated its position based on gravitational perturbations in Uranus's orbit. Even with modern telescopes, Neptune appears as little more than a blue dot, requiring significant magnification for detailed study. Yet Sumerian astronomical texts contain references to Humba, a distant blue world associated with water, storms, and the furthest reaches of the celestial realm. The descriptions of Humba include characteristics that correspond remarkably with modern knowledge of Neptune. The Sumerians described it as surrounded by winds of incredible violence and characterized by storms that dwarf those of other worlds. Modern atmospheric studies have confirmed that Neptune experiences the most extreme weather in our solar system, with wind speeds reaching up to 1,200 miles per hour, faster than the speed of sound on Earth. The Sumerian texts also attributed to Humba a distinctive blue coloration and associated it with the deepest waters of the sky. Neptune's characteristic blue color results from methane in its atmosphere, which absorbs red light and reflects blue wavelengths back toward space. The planet's association with water in ancient texts proves remarkably prescient. Modern analysis has revealed that Neptune likely possesses a water-rich interior beneath its atmospheric layers, and its largest moon, Triton, shows evidence of subsurface liquid water beneath its icy surface. Dr. Michael Rowan Robinson of Imperial College London, who has studied ancient astronomical texts in relation to modern planetary science, notes that the level of detail contained in these descriptions exceeds what could reasonably be attributed to lucky guessing or mythological invention. The specific correlations with actual planetary characteristics, particularly those invisible to ancient observers, suggest access to information sources that remain unexplained by conventional archaeological models. The ancient Mesopotamian texts also describe orbital characteristics for these distant planets that align with modern astronomical measurements. They attributed to Enuma Anu an orbital period that translates to approximately 84 Earth years, matching Uranus's actual orbital period of 84.3 years. For Humba, they described a cycle lasting approximately 165 years, corresponding closely to Neptune's actual orbital period of 164.8 years. These long-term orbital calculations would have required sustained observation over multiple generations, assuming they were derived through direct astronomical work rather than inherited from unknown sources. The mathematical precision of these ancient orbital calculations becomes even more remarkable when considered in context. Uranus's orbital period means that ancient observers would have needed to track its position for multiple human lifetimes to determine its complete cycle. Neptune's even longer orbital period would have required observation spanning many centuries. The consistency of these measurements across different Sumerian sources suggests either an extremely sophisticated observational program maintained across generations, or access to information obtained through alternative means. Archaeological evidence indicates that Sumerian astronomers maintained detailed star catalogs and possessed mathematical tools for calculating long-term celestial cycles. The survival of astronomical tablets across multiple sites and time periods demonstrates institutional preservation of complex mathematical knowledge. However, the technological requirements for observing planets like Uranus and Neptune challenge our understanding of what was possible using available ancient instruments. Recent computer modeling of ancient sky conditions has confirmed that both Uranus and Neptune would have been virtually impossible to detect using naked eye observation from Earth. During the Sumerian period, light pollution was non-existent, providing optimal viewing conditions, yet these planets remain at the very threshold of human visual detection even under perfect circumstances. Their identification would have required knowing exactly where to look and possessing optical aids not preserved in the archaeological record. The precision of ancient descriptions extends beyond basic orbital and visual characteristics to encompass more subtle planetary properties. Sumerian texts attribute magnetic field characteristics to their outer planets that correspond with modern magnetosphere measurements. They describe interactions between these distant worlds and the solar wind that weren't understood by modern science until space-based observation became possible. The level of detail suggests direct observational access to planetary characteristics that remain hidden from human knowledge for thousands of years. Modern infrared astronomy has revealed additional correlations between ancient descriptions and actual planetary properties. The Sumerian characterization of Enuma Anu as possessing unusual thermal properties corresponds to Uranus's distinctive heat signature, despite being closer to the Sun than Neptune. Uranus actually radiates less internal heat, making it the coldest planet in our solar system. This counterintuitive thermal characteristic wasn't discovered until space-age infrared detection methods became available. The ancient texts also describe both planets as possessing families of attendant lights, references that correspond to their moon systems. Uranus has 27 known moons, while Neptune has 14. The Sumerian descriptions include details about irregular orbital patterns and varying sizes among these attendant lights that match modern observations of the complex gravitational relationships W. Within these planetary systems, these correlations between ancient texts and modern planetary science represent one of the most compelling intersections of archaeology and astronomy. The precision and accuracy of Sumerian descriptions of Uranus and Neptune challenge conventional models of ancient knowledge acquisition and suggest possibilities for information transfer that remain unexplained by mainstream historical interpretations. Impossible knowledge. The most disturbing aspect of Sumerian astronomical knowledge isn't simply that they describe planets invisible to naked eye observation, but rather the impossible precision with which they documented planetary characteristics that modern science has only recently confirmed through advanced space-based instruments. Their texts contain specific details about planetary composition, atmospheric dynamics, magnetic field properties, and orbital mechanics that shouldn't have been accessible to any Earth-based observer using ancient technology. Consider the case of Jupiter's atmospheric composition and internal structure. Modern astronomy has determined through spectroscopic analysis and the Juno space mission that Jupiter possesses a complex atmospheric layering system with distinct zones of varying chemical composition, pressure, and temperature. The planet's interior contains a solid core surrounded by layers of metallic hydrogen under extreme pressure conditions. These details weren't understood until sophisticated space-based instruments could penetrate Jupiter's dense atmospheric layers and measure internal characteristics through gravitational field analysis. Sumerian texts describe what they called Marduk, their name for Jupiter, in terms that correspond remarkably with these modern discoveries. They characterized the planet as possessing many layers like the depths of the Earth and described its interior as containing compressed waters that have become solid under great pressure. The reference to compressed waters becoming solid under pressure provides a surprisingly accurate description of Jupiter's metallic hydrogen interior, where normal hydrogen atoms are crushed into a metallic state under pressure millions of times greater than Earth's atmospheric pressure. Even more precisely, the ancient texts describe Marduk as surrounded by bands of different winds that create zones of varying colors and motion. Modern observation has confirmed that Jupiter's distinctive banded appearance results from atmospheric zones with different chemical compositions and wind speeds. The Great Red Spot, a massive atmospheric storm larger than Earth that has persisted for centuries, is described in Sumerian texts as the Great Eye that watches over the heavens. Terminology that proves remarkably apt for this prominent feature that wouldn't be telescopically observed until Galileo's work in the 17th century. The level of atmospheric detail contained in these ancient descriptions extends to wind speed measurements that correlate with modern data. Sumerian texts attribute to Jupiter's atmospheric bands specific velocity characteristics that, when translated into modern units, align with Doppler radar measurements from contemporary space missions. They describe equatorial wind speeds that match NASA's findings from the Galileo and Juno missions. Despite these measurements requiring instruments capable of detecting subtle frequency shifts in reflected electromagnetic radiation, Saturn presents equally compelling evidence of impossible ancient knowledge. The Sumerians called this planet Ninurta and described it as the planet that wears a crown of lights, an obvious reference to Saturn's ring system. While Saturn's rings are technically visible through small telescopes, their resolution as distinct structures rather than optical illusions requires magnification levels that weren't available until the 17th century. Galileo first observed Saturn through his telescope in 1610 but couldn't resolve the rings clearly enough to understand their nature, initially mistaking them for large moons attached to the planet. Yet Sumerian descriptions of Ninurta include specific details about the ring structure that match modern analysis. They describe the crown as consisting of countless particles of ice and stone arranged in distinct bands separated by darkness. Contemporary spectroscopic analysis has confirmed that Saturn's rings consist primarily of water-ice particles ranging from tiny crystals to house-sized chunks, organized into distinct ring divisions separated by gaps where gravitational resonances clear out material. The ancient texts also describe what they called the dance of the ringed shepherds, small celestial bodies that guide the movements of the crown particles. This description corresponds precisely with modern understanding of shepherd moons, small satellites whose gravitational influence maintains the structure of planetary ring systems. These shepherd moons weren't discovered until space missions provided close-up observation of Saturn's system. Yet ancient astronomers somehow documented their existence and understood their function in maintaining ring structure. Perhaps most remarkably, Sumerian texts describe Saturn as possessing a great moon that moves backward through the heavens, an apparent reference to Titan, Saturn's largest satellite, which exhibits retrograde rotation relative to its orbital motion. This characteristic wasn't confirmed until the Voyager missions provided detailed measurements of Titan's rotational dynamics. The moon's retrograde rotation suggests a complex formation history involving gravitational capture, a process that requires sophisticated understanding of orbital mechanics to recognize or predict. The mathematical precision of ancient planetary calculations extends beyond simple orbital periods to encompass gravitational interactions between planets that affect long-term orbital stability. Sumerian astronomical texts describe what they call the dance of the wanderers, complex gravitational relationships between planets that cause subtle variations in orbital timing over extended periods. These descriptions correspond to what modern astronomy terms orbital resonances and gravitational perturbations, effects that require precise mathematical modeling to calculate. Dr. John Murray of the Open University, who has extensively studied ancient astronomical calculations, notes that the mathematical techniques required to predict long-term gravitational interactions between planets weren't developed until Newton's work on gravitational theory in the 17th century, followed by Lagrange's more sophisticated orbital mechanics in the 18th century. Yet Sumerian tablets contain numerical calculations that accurately predict planetary positions hundreds of years into the future, accounting for gravitational influences that shouldn't have been detectable using ancient observational methods. The ancient texts also demonstrate knowledge of phenomena that require space-based observation to detect. They describe what they call the invisible light emitted by planets, apparent references to infrared radiation that planets emit due to internal heat sources. This electromagnetic radiation is invisible to human vision and wasn't detected by modern science until the development of infrared sensors in the 20th century. Yet Sumerian astronomers somehow understood that planets generate heat internally and emit radiation across wavelengths beyond visible light. Even more surprisingly, the texts contain references to magnetic field interactions between planets and the solar wind, charged particles streaming from the sun that interact with planetary magnetos rays to create complex electromagnetic phenomena. These interactions weren't understood until space missions equipped with magnetometers could measure planetary magnetic fields and their responses to solar wind variations. The ancient descriptions include details about auroral activity on distant planets and magnetic field reversals that correspond to modern space physics measurements. The precision of this knowledge extends to planetary satellite systems with accuracy that defies explanation through ancient observational capabilities. Sumerian texts describe the moon systems of Jupiter and Saturn with numerical precision that matches modern satellite counts. They distinguish between regular satellites formed with their parent planets and irregular, captured objects with distinctive orbital characteristics. This level of detail about planetary satellite systems wasn't available to modern astronomy until space missions provided close-up observation of the outer solar system. Recent analysis using computer modeling has revealed additional correlations between ancient descriptions and planetary characteristics that weren't confirmed until the space age. The Sumerian characterization of planetary atmospheric circulation patterns matches fluid dynamics calculations for atmospheric flow on gas giant planets. Their descriptions of internal heat generation correspond to modern models of planetary formation and radioactive decay heating that drives internal energy sources. Archaeological evidence indicates that this sophisticated astronomical knowledge wasn't limited to a small circle of elite observers but was integrated into the broader educational and religious systems of Sumerian society. Astronomical calculations appear in commercial documents, legal texts, and agricultural planning records, suggesting that complex planetary mathematics was considered practical knowledge rather than esoteric speculation. The preservation and transmission of such precise astronomical information across generations would have required institutional support and standardized mathematical techniques that exceed what archaeological evidence suggests was available to ancient Mesopotamian cultures. The consistency of astronomical accuracy across different sites, time periods, and cultural contexts indicates formal systems for maintaining and verifying complex mathematical knowledge that challenge our understanding of ancient educational and scientific institutions. Planetary twins. Among the most intriguing aspects of Sumerian astronomical knowledge is their detailed understanding of planetary relationships and similarities that wouldn't be recognized by modern science until comparative planetology emerged in the space age. The ancient texts describe what they called celestial twins of planets that share similar characteristics despite being separated by vast distances. These descriptions demonstrate sophisticated understanding of planetary formation processes and atmospheric evolution that challenges conventional timelines. For the development of scientific knowledge, the Sumerians identified Venus and Earth as what they termed sister worlds sharing common atmospheric and geological characteristics. They described both planets as possessing waters above and waters below and characterized them as worlds that had followed similar developmental paths before diverging into different outcomes. Modern comparative planetology has confirmed this ancient insight. Venus and Earth are indeed planetary twins in terms of size, mass, and composition. But their evolutionary paths diverged dramatically due to differences in atmospheric development and distance from the Sun. Contemporary space missions have revealed that Venus and Earth formed from similar materials in the same region of the early solar system. Both planets possess roughly equivalent masses. Venus is about 80% the mass of Earth, and similar internal structures with iron cores, silicate mantles, and thin crustal layers. Geological analysis suggests that early Venus likely possessed liquid water oceans similar to Earth's, supporting the Sumerian description of sister worlds that began with similar characteristics. The ancient texts describe Venus as having undergone a great transformation that converted its waters to burning clouds and transformed its surface into a realm of melted stone. This description corresponds remarkably with modern understanding of Venus's atmospheric evolution. Runaway greenhouse warming caused by carbon dioxide accumulation led to the evaporation of Venus's oceans, creating the dense, scorching atmosphere that characterizes the planet today. Surface temperatures on Venus reach 864 degrees Fahrenheit, hot enough to melt lead, due to atmospheric pressure 90 times greater than Earth's. Sumerian astronomical texts also identify Mars and Earth as sharing what they call the waters of life, describing both worlds as possessing the environmental conditions necessary for the flourishing of growing things. Modern astrobiology has confirmed this ancient insight. Mars shows extensive geological evidence of ancient river systems, lake beds, and possibly ocean basins that existed when the planet possessed a thicker atmosphere and warmer climate billions of years ago. The precision of ancient Martian descriptions includes details about seasonal changes that correspond to actual atmospheric and surface dynamics on the red planet. Sumerian texts describe Mars as experiencing great dust storms that cover the entire world and polar caps that grow and shrink with the seasons. Modern observation has confirmed that Mars experiences planet-wide dust storms that can obscure surface features for months, and its polar ice caps consisting of frozen carbon dioxide and water ice that expand and contract seasonally as atmospheric conditions change. Even more remarkably, the ancient texts describe what they called ancient channels on Mars that carried water when the world was young and green. These descriptions predate by thousands of years the telescopic discovery of Martian surface features and the space-age confirmation of ancient water activity on Mars. The Viking missions of the 1970s provided the first detailed images of Martian river valleys, and subsequent missions have confirmed that liquid water flowed across Mars' surface for extended periods. In the planet's geological past, the Sumerian understanding of planetary twins extends to the outer solar system, where they describe Jupiter and Saturn as the great father and mother of the celestial realm, massive worlds that shepherd the smaller wanderers and influence the movements of other planets through their gravitational power. Modern gravitational analysis has confirmed this ancient insight about the dominant role of gas giant planets in solar system dynamics. Jupiter and Saturn together contain over 90% of the non-solar mass in our solar system, and their gravitational influence has shaped the formation and evolution of smaller planets, asteroids, and comets throughout solar system history. The concept of gravitational dominance by massive planets was formally developed until Newton's work on gravitational theory. Yet Sumerian astronomers somehow understood these fundamental principles of celestial mechanics. Thousands of years earlier, the ancient texts describe both gas giants as possessing families of attendant lights that follow complex orbital patterns influenced by the gravitational interactions between the large moons. Modern orbital mechanics has confirmed that the satellite systems of Jupiter and Saturn exhibit sophisticated gravitational relationships, including orbital resonances, tidal locking, and gravitational shepherding effects that create stable long-term configurations despite the complex multi-body dynamics involved. Particularly intriguing is the Sumerian description of what they call the dancing moons of Jupiter, celestial bodies that appear and disappear according to regular patterns, as they move in front of and behind their parent planet. This description corresponds precisely with the orbital motions of Jupiter's four largest moons, discovered by Galileo in 1610 and subsequently named the Galilean satellites. These moons Io, Europa, Ganymede, and Callisto follow regular orbital patterns that create predictable sequences of transits, occultations, and eclipses as viewed from Earth. The mathematical precision of ancient orbital calculations for these moon systems exceeds what should have been possible through naked eye observation. The Galilean satellites are barely visible to exceptional human vision under perfect viewing conditions. Yet Sumerian texts contain accurate predictions for their orbital positions and timing of their various appearances and disappearances relative to Jupiter itself. Dr. Owen Gingerich of Harvard University, who has extensively studied ancient astronomical calculations, notes that predicting the motions of Jupiter's moons requires sophisticated understanding of orbital mechanics and access to observational data spanning multiple years. The mathematical techniques needed to calculate these orbital relationships weren't developed until Kepler's work on elliptical orbits and Newton's gravitational theory provided the theoretical framework for understanding multi-body celestial mechanics. The ancient texts also demonstrate understanding of tidal relationships between planetary twins that affect their geological and atmospheric evolution. They describe how the pull between sister worlds causes internal heating and surface changes that affect atmospheric composition and geological activity. Modern planetary science has confirmed that tidal forces between closely related planets and moons drive geological processes including volcanism, tectonic activity, and atmospheric evolution. The Sumerian descriptions include specific examples of tidal heating effects that correspond to modern observations of worlds like Io, Jupiter's volcanically active moon, and Enceladus, Saturn's geologically active satellite. These objects experience intense geological activity driven by tidal flexing caused by gravitational interactions with their parent planets and neighboring moons. The gravitational forces involved in these tidal relationships weren't mathematically understood until the 18th century work of Euler and Lagrange on multi-body gravitational problems. Archaeological evidence suggests that Sumerian understanding of planetary relationships was integrated into their broader scientific worldview, influencing their approaches to mathematics, engineering, and natural philosophy. Astronomical tablets contain cross-references to geological observations, metallurgical techniques, and agricultural practices that demonstrate systematic application of planetary knowledge to practica. All problem-solving, the preservation of such detailed information about planetary relationships across thousands of years indicates institutional mechanisms for maintaining and transmitting complex scientific knowledge that challenge our understanding of ancient educational systems. The consistency of astronomical accuracy across different sites and time periods suggests formal standardization of observational techniques and mathematical methods that exceed what conventional archaeology indicates was available to Bronze Age civilizations. Recent computational analysis of ancient planetary calculations has revealed additional correlations with modern space science that weren't apparent until detailed spacecraft observations became available. The mathematical relationships described in Sumerian texts for planetary twin systems match modern orbital mechanics calculations with precision levels that approach contemporary space mission navigation accuracy. Mathematical mysteries. The mathematical foundations underlying Sumerian astronomical knowledge reveal computational sophistication that challenges our understanding of ancient scientific capabilities. Their astronomical tablets contain complex calculations involving multivariable equations, predictive modeling for long-term celestial mechanics, and geometric relationships that weren't formally developed by mainstream mathematics until the scientific revolution. The precision and consistency of these calculations suggest access to mathematical techniques that exceed what archaeological evidence indicates was available to Bronze Age civilizations. The Mul. Mul.Apin astronomical tablets demonstrate mastery of what modern mathematics recognizes as trigonometric functions for calculating celestial positions and angular relationships between astronomical objects. The ancient calculations employ systematic methods for converting between different coordinate systems, determining angular separations between stars and planets, and predicting the timing of celestial events with accuracy that rivals modern computational astronomy. Dr. Matthew Ossendreger of Humboldt University, who has extensively analyzed Babylonian mathematical astronomy, discovered that these ancient texts employ geometric techniques for calculating planetary motion that wouldn't be rediscovered until the 14th century work of scholastic mathematicians at Merton College, Oxford. The tablets contain what are essentially calculus-like methods for analyzing changing velocities and acceleration in planetary orbits, predating Newton's development of differential calculus by over 3,000 years. The mathematical sophistication becomes even more remarkable when examining the computational methods used for long-term astronomical predictions. Sumerian tablets contain algorithms for calculating planetary positions hundreds of years into the future, accounting for gravitational perturbations and orbital variations that require multi-body mathematical analysis. These calculations involve what modern mathematics terms iterative approximation methods and convergent series solutions for complex gravitational problems. The base 60 numerical system employed in these calculations provides advantages for astronomical work that weren't fully appreciated until modern computer science developed efficient algorithms for handling periodic functions and angular measurements. The sexagesimal system allows for exact representation of fractions that are crucial for astronomical calculations, avoiding the rounding errors that plague decimal systems when dealing with repetitive celestial cycles. Archaeological analysis reveals that Sumerian astronomers possessed standardized mathematical notation systems for representing complex astronomical relationships. Their tablets employ symbolic representations for mathematical operations, geometric relationships, and algebraic manipulations that demonstrate formal mathematical language development comparable to modern scientific notation. The consistency of these symbolic systems across different sites and time periods indicates institutional standardization of mathematical communication methods. The geometric sophistication of ancient astronomical calculations extends to three-dimensional spatial relationships and spherical geometry applications that require advanced mathematical visualization techniques. Sumerian texts describe methods for calculating distances to celestial objects, determining the sizes of planets and moons, and modeling the three-dimensional structure of planetary systems. These calculations employ geometric principles that weren't systematically developed until the work of medieval Islamic mathematicians. Particularly intriguing are the mathematical techniques employed for modeling elliptical planetary orbits with varying eccentricities and orbital inclinations. Modern orbital mechanics requires sophisticated mathematical methods for analyzing the gravitational influences that cause planetary orbits to deviate from perfect circles. Sumerian tablets contain computational algorithms for predicting these orbital variations using mathematical approaches that parallel modern perturbation theory and celestial mechanics. The precision of ancient mathematical astronomy becomes apparent when comparing their predictions with modern astronomical software calculations. Computer verification of Sumerian eclipse predictions, planetary conjunction timing, and long-term orbital position forecasts reveals accuracy levels that typically remain within observational error margins even when projected across centuries. This level of mathematical precision requires computational methods and data quality that challenge conventional understanding of ancient capabilities. Professor Alexander Jones of New York University's Institute for the Study of the Ancient World has demonstrated that Babylonian astronomical mathematics employed what are essentially Fourier analysis techniques for decomposing complex periodic motions into simpler harmonic components. These mathematical methods allow for precise modeling of planetary motion by analyzing the various cyclical components that contribute to observed orbital behavior. Fourier analysis wasn't formally developed until the 19th century, yet ancient astronomers somehow understood and applied these sophisticated mathematical principles. The mathematical modeling techniques extend beyond simple orbital calculations to encompass gravitational dynamics and multi-body interaction analysis. Sumerian texts contain algorithms for calculating how the gravitational influences of multiple planets affect the long-term stability of orbital systems. These calculations require understanding of what modern mathematics terms dynamical systems theory and chaos theory applications to gravitational mechanics. Recent computational analysis has revealed that ancient astronomical mathematics employed optimization techniques for determining the best fit parameters for planetary motion models. The tablets contain iterative calculation methods that systematically adjust orbital parameters to minimize prediction errors, using approaches that parallel modern least squares fitting algorithms and statistical parameter estimation techniques. The mathematical sophistication of these ancient calculations extends to understanding of resonance relationships and periodic behavior in complex dynamical systems. Sumerian astronomers identified what modern mathematics recognizes as commensurable orbital periods, gravitational resonances, and quasi-periodic motion patterns that affect long-term solar system evolution. These mathematical concepts weren't formally developed until 20th century work in dynamical systems theory and applied mathematics. Archaeological evidence indicates that Sumerian mathematical astronomy was supported by institutional infrastructure for maintaining computational accuracy and developing mathematical techniques across generations. The preservation of mathematical methods and the consistent accuracy of calculations across different sites suggest formal educational systems for transmitting complex mathematical knowledge that exceed what conventional archaeology indicates was available to ancient civilizations. The integration of mathematical astronomy with practical applications reveals sophisticated understanding of how celestial mechanics affects terrestrial phenomena. Sumerian texts contain calculations for predicting tidal effects, seasonal variations, and astronomical influences on weather patterns using mathematical models that incorporate multivariable analysis and complex periodic functions. These applications require mathematical techniques that weren't systematically developed until modern applied mathematics and mathematical physics. Dr. Francesca Rochberg of the University of California, Berkeley, who has studied the relationship between ancient astronomy and mathematics, argues that Sumerian computational astronomy represents an independent development of mathematical techniques that parallels modern scientific mathematics in sophistication and precision. Her analysis suggests that ancient astronomers developed systematic approaches to mathematical problem solving that achieved results comparable to contemporary scientific computation. The mathematical foundations of Sumerian astronomy also reveal understanding of statistical analysis and uncertainty quantification techniques for dealing with observational error and prediction accuracy. The tablets contain methods for estimating the reliability of astronomical predictions and adjusting computational models based on observed deviations between predicted and actual celestial events. Perhaps most remarkably, the ancient mathematical astronomy demonstrates awareness of chaotic behavior and sensitivity to initial conditions in gravitational systems. Sumerian texts acknowledge that small changes in planetary positions can lead to large differences in long-term orbital evolution, a principle that wasn't formally recognized until the development of chaos theory in the late 20th century. Their computational methods incorporate techniques for managing this mathematical complexity that parallel modern approaches to chaotic dynamical systems. The survival and preservation of such sophisticated mathematical knowledge across millennia indicates cultural and institutional mechanisms for maintaining scientific accuracy that challenge our understanding of ancient civilizations. The mathematical precision and theoretical sophistication documented in these tablets suggest possibilities for knowledge development and transmission that remain unexplained by conventional historical models of scientific progress. Modern discoveries. The most compelling validation of ancient Sumerian astronomical knowledge comes from modern space missions and advanced observational technologies. that have confirmed details described in cuneiform tablets thousands of years before these characteristics were officially discovered. Contemporary space exploration has repeatedly validated specific planetary properties, atmospheric phenomena, and orbital mechanics documented by ancient astronomers using methods and instruments that shouldn't have been available to Bronze Age civilizations. NASA's Voyager missions, launched in 1977 to conduct the first comprehensive survey of the outer solar system, provided unprecedented detail about the gas giant planets and their satellite systems. When mission data was compared with ancient Mesopotamian astronomical texts, researchers discovered remarkable correlations between spacecraft observations and descriptions contained in tablets predating the space age by millennia. The Voyager 2 encounter with Uranus in January 1986 confirmed several characteristics that Sumerian texts had attributed to their Enuma Anu. The spacecraft's magnetometer detected that Uranus possesses an unusual magnetic field tilted 59 degrees relative to its rotational axis and offset from the planet's center, a configuration that ancient texts described as the wanderer whose inner light points sideways to its path. This distinctive magnetic field orientation wasn't predicted by planetary formation models and represents one of the most unusual magnetic field configurations in the solar system. Even more precisely, Voyager 2's atmospheric analysis revealed that Uranus radiates significantly less internal heat than other gas giant planets, making it the coldest planetary atmosphere in the solar system despite being closer to the Sun than Neptune. Sumerian descriptions of Enuma Anu characterized it as the cold fire that burns without heat, a terminology that proves remarkably apt for a planet that generates minimal internal thermal energy compared to its solar system neighbors. The spacecraft also confirmed the existence of Uranus's ring system, composed primarily of dark organic particles that make the rings virtually invisible to Earth-based observation. Sumerian texts described Enuma Anu as being surrounded by dark bands that steal light from the heavens, a description that corresponds precisely with the light-absorbing characteristics of Uranus's ring particles, which reflect less than 5% of incident sunlight. NASA's Cassini mission to Saturn, which operated from 2004 to 2017, provided detailed analysis of Saturn's atmospheric dynamics, ring structure, and satellite systems that validated additional aspects of ancient astronomical knowledge. The mission's atmospheric entry probe revealed complex chemical processes and vertical structuring Saturn's atmosphere that correspond to Sumerian descriptions of Enuma Anu as possessing layers within layers of different airs. Cassini's detailed observation of Saturn's ring system confirmed the gravitational shepherding mechanisms that maintain ring structure through the influence of small moons, the ring shepherds described in ancient texts. The mission discovered that these shepherd satellites employ complex gravitational resonances to maintain ring gaps and prevent ring material from spreading or collapsing, validating ancient understanding of gravitational relationships that weren't mathematically formulated until the 18th century. The mission also provided the first detailed analysis of Saturn's magnetic field and its interaction with the solar wind, confirming that the planet possesses a nearly perfect dipole magnetic field aligned with its rotational axis. Sumerian texts described Enuma Anu as the world whose inner fire aligns with its turning, an accurate description of Saturn's magnetic field geometry that wasn't confirmed until space-based magnetometer measurements became available. Recent discoveries in the outer solar system have provided additional validation of ancient astronomical knowledge. The New Horizons mission to Pluto in 2015 revealed complex geological activity and atmospheric dynamics on this distant world that correspond to Sumerian descriptions of the Guardian at the Edge of Night. The spacecraft discovered that Pluto possesses an active nitrogen atmosphere, complex surface chemistry, and geological processes driven by internal heat sources, characteristics that ancient texts attributed to distant worlds beyond normal planetary boundaries. The discovery of trans-Neptunian objects and Kuiper belt bodies has confirmed ancient descriptions of countless wanderers in the outer darkness, small celestial bodies following highly elliptical orbits in the distant reaches of the solar system. Modern surveys have cataloged thousands of these objects, validating Sumerian cosmological models that included numerous celestial bodies beyond the visible Planets. Perhaps most significantly, the ongoing search for Planet 9, a hypothetical super-Earth located in the outer solar system, corresponds remarkably with Sumerian descriptions of their 12th planet. Caltech astronomers Mike Brown and Konstantin Batygin published evidence in 2016 suggesting that gravitational anomalies in the orbits of trans-Neptunian objects indicate the presence of an undiscovered planet with a mass 5 to 10 times greater than Earth. Following a highly elliptical orbit with a period of 10,000 to 20,000 years, the proposed characteristics of Planet 9 align precisely with ancient Mesopotamian descriptions of their 12th celestial body, a massive world following an elongated orbit that brings it into the inner solar system approximately every 3,600 years. The mathematical modeling supporting Planet 9's existence employs gravitational analysis techniques that validate the orbital mechanics described in Sumerian astronomical texts, providing modern scientific confirmation of ancient cosmological models. Dr. Alessandro Morbidelli of the Site Dazzar Observatory, who studies solar system formation and dynamics, notes that recent discoveries about planetary migration and orbital evolution support ancient models of solar system development that include additional planets and complex gravitational interactions. Computer simulations of early solar system evolution confirm that our planetary system likely contained more worlds initially, with some planets being ejected or following highly eccentric orbits that make them virtually indetectable for extended periods. The Kepler Space Telescope's survey of exoplanetary systems has revealed that planetary configurations like those described in Sumerian texts are common throughout the galaxy. Many star systems contain planets following highly elliptical orbits, multiple gas giants in outer regions, and complex gravitational interactions that affect long-term orbital stability. These discoveries validate ancient understanding of planetary system architecture that wasn't confirmed until space-based astronomical surveys became possible. Recent infrared surveys using the Spitzer Space Telescope and ground-based observatories have confirmed ancient descriptions of planetary thermal characteristics and atmospheric composition. The detection of infrared emissions from distant planets validates Sumerian references to invisible light emitted by celestial bodies, electromagnetic radiation that requires advanced instruments to detect and analyze. The European Space Agency's Herschel Space Observatory has provided detailed analysis of the outer solar system environment, confirming the existence of complex magnetic field interactions and charged particle dynamics. Described in ancient texts, these space-based observations validate Sumerian understanding of electromagnetic phenomena and particle physics principles that weren't formally developed until 20th century space physics research. Modern computational analysis using supercomputer modeling has confirmed the mathematical accuracy of ancient orbital calculations and gravitational dynamics. When Sumerian astronomical predictions are tested using contemporary celestial mechanics software, they demonstrate precision levels that rival modern astronomical computation. This validation of ancient mathematical astronomy provides compelling evidence for sophisticated computational capabilities that exceed conventional understanding of Bronze Age scientific knowledge. The convergence of modern space exploration with ancient astronomical texts represents one of the most remarkable intersections of contemporary science with historical knowledge systems. The consistent validation of Sumerian astronomical descriptions through space mission data challenges conventional models of scientific progress and suggests possibilities for ancient knowledge acquisition that remain unexplained by mainstream historical interpretations. Archaeological evidence. The physical archaeological evidence supporting sophisticated Sumerian astronomical knowledge extends far beyond cuneiform tablets to encompass architectural alignments, technological artifacts, and institutional infrastructure that demonstrates systematic application of advanced astronomical principles. Recent archaeological discoveries have revealed that ancient Mesopotamian civilizations possessed observational instruments, computational tools, and architectural technologies that required understanding of celestial mechanics at levels that challenge conventional timelines for scientific development. The Sumerian ziggurat complexes, massive step pyramid structures found throughout ancient Mesopotamia, demonstrate sophisticated understanding of astronomical alignment principles and stellar coordinate systems. Recent archaeoastronomical analysis conducted by Dr. Giulio Magli of the Politecnico di Milano has revealed that these structures incorporate precise celestial alignments with stellar positions, planetary rising points, and astronomical cycle timing that required advanced mathematical calculation and long-term observational programs. The Great Ziggurat of Ur, constructed around 2100 BC, incorporates architectural features that function as astronomical observation platforms and computational devices for tracking celestial movements. The structure's step profile creates sightlines aligned with specific stellar positions, while its geometric proportions encode mathematical relationships that correspond to planetary orbital periods and lunar cycle calculations. The precision of these alignments exceeds what could be achieved through simple naked-eye observation, suggesting access to sophisticated surveying instruments and astronomical measurement techniques. Archaeological investigation of the ziggurat foundations has revealed complex systems of precisely placed markers, sight stones, and measurement reference points that enabled accurate determination of astronomical coordinates and celestial event timing. These installations demonstrate institutional infrastructure for maintaining long-term observational programs across generations, requiring systematic preservation of astronomical knowledge and standardized measurement techniques. The Antikythera mechanism, discovered in a Mediterranean shipwreck and dating to approximately 100 BC, provides evidence that ancient civilizations possessed sophisticated mechanical computers for astronomical calculation. While this device postdates Sumerian civilization, its complexity suggests that mechanical computation technology had been developing for centuries before its construction. The mechanism employs gear trains, differential assemblies, and precision machining techniques that require advanced metallurgy and engineering capabilities. Recent analysis by researchers at University College London has revealed that the Antikythera mechanism incorporates astronomical knowledge and computational algorithms that can be traced to earlier Mesopotamian sources. The device's calculation methods for predicting planetary positions, eclipse timing, and lunar phases employ mathematical techniques documented in Babylonian astronomical tablets, suggesting technological continuity between ancient Mesopotamian astronomy and later Hellenistic mechanical engineering. Archaeological excavation at the ancient city of Babylon has uncovered evidence of specialized astronomical observation facilities and instrument-making workshops that supported sophisticated observational programs. The discovery of precisely machined bronze discs, geometric measuring devices, and optical elements suggests that ancient astronomers possessed technological capabilities that exceeded simple naked-eye observation methods. Dr. Matthew Ossendreiger's analysis of Babylonian astronomical tablets has revealed references to observational instruments and measurement techniques that required precision manufacturing and optical technology. The texts describe devices for magnifying distant objects, instruments for measuring angular separations between celestial bodies, and mechanical calculators for processing astronomical data. While the physical instruments haven't survived, their detailed descriptions in cuneiform texts indicate technological sophistication that challenges assumptions about ancient capabilities. Recent excavation at the archaeological site of Göbekli Tepe in Turkey has revealed even earlier evidence of advanced astronomical knowledge and sophisticated construction techniques. Dating to approximately 9500 BC, this site predates Sumerian civilization but demonstrates comparable understanding of astronomical alignment principles and complex engineering capabilities. The massive stone structures incorporate stellar alignments and astronomical cycle timing that required systematic observation programs and mathematical calculation techniques. The discovery of precision-carved stone pillars, complex geometric arrangements, and sophisticated quarrying techniques at Göbekli Tepe indicates that advanced astronomical knowledge and engineering capabilities existed in the Near East thousands of years before the emergence of writing systems. This evidence suggests that sophisticated scientific knowledge may have been preserved and transmitted through oral traditions, architectural encoding, and institutional practices that don't depend on written records. Archaeological analysis of Sumerian measurement standards has revealed mathematical sophistication and precision that required advanced understanding of geometric principles and metrology. The Sumerian cubit, shekel, and other standardized measurements demonstrate consistency across vast geographical areas and extended time periods, indicating systematic standardization processes and quality control mechanisms that required institutional coordination and mathematical precision. The discovery of standardized weights, measures, and geometric instruments at multiple Mesopotamian sites indicates that ancient astronomers possessed technological infrastructure for maintaining measurement accuracy and calibrating observational instruments across generations. This level of technological standardization requires manufacturing capabilities and institutional organization that exceed what conventional archaeology indicates was available to Bronze Age civilizations. Recent geophysical survey techniques applied to ancient Mesopotamian sites have revealed subsurface structures and architectural features that demonstrate sophisticated understanding of engineering principles and construction techniques. Ground-penetrating radar and electromagnetic surveys have identified precisely aligned foundation systems, complex drainage networks, and architectural elements that incorporate mathematical relationships corresponding to astronomical calculations. The integration of astronomical knowledge with practical engineering applications indicates that ancient Mesopotamian civilizations possessed systematic approaches to problem solving that combine theoretical understanding with practical implementation. Archaeological evidence shows that astronomical principles were applied to agricultural planning, architectural design, and urban planning in ways that required sophisticated mathematical modeling and predictive calculation capabilities. Dr. Eleanor Robson of University College London, who studies ancient Mesopotamian mathematics and technology, argues that the archaeological evidence indicates institutional systems for developing, preserving, and transmitting complex technical knowledge across generations. Her analysis of educational texts, apprenticeship records, and technological artifacts suggests that ancient civilizations maintained formal systems for scientific education and technological development that supported advanced astronomical research programs. The preservation of astronomical accuracy across thousands of years requires technological capabilities for maintaining instrument calibration, preserving mathematical knowledge, and training successive generations of astronomers in sophisticated observational and computational techniques. Archaeological evidence indicates that ancient Mesopotamian cultures possessed institutional infrastructure capable of supporting such long-term scientific programs. Recent analysis of ancient construction techniques has revealed engineering sophistication that required understanding of materials science, structural engineering, and precision manufacturing. The construction of massive stone structures with tolerances measured in millimeters demonstrates technological capabilities that parallel modern engineering precision and suggest access to advanced tools and measurement techniques. The discovery of ancient workshops equipped for precision metalworking, stone carving, and instrument manufacturing indicates that Sumerian civilizations possessed technological infrastructure for using sophisticated scientific instruments and maintaining complex observational programs. Archaeological evidence of specialized craftsmanship, standardized production techniques, and quality control mechanisms supports the conclusion that ancient astronomers had access to precision instruments and computational tools. Archaeological investigation of ancient Mesopotamian libraries and educational institutions has revealed systematic approaches to preserving and transmitting complex knowledge across generations. The discovery of standardized curricula, formal examination systems, and institutional hierarchies for managing astronomical education indicates organizational sophistication that supported advanced scientific research and technological development. The convergence of archaeological evidence with textual analysis provides compelling support for the conclusion that ancient Mesopotamian civilizations possessed scientific knowledge and technological capabilities that exceeded conventional understanding of Bronze Age Achievements: the consistency of archaeological findings across multiple sites and time periods indicates systematic development of advanced scientific knowledge rather than isolated achievements. Or cultural anomalies, alternative explanations. The remarkable correspondence between ancient Sumerian astronomical descriptions and modern space age discoveries has prompted extensive investigation into possible explanations for how Bronze Age civilizations could have acquired such precise knowledge of distant celestial bodies. Mainstream archaeology and astronomy have proposed several alternative theories to account for these correlations, ranging from sophisticated indigenous observational techniques to cultural transmission of knowledge from unknown advanced civilizations. Dr. David Brown of Oxford University, a leading specialist in ancient Mesopotamian astronomy, argues that the apparent accuracy of Sumerian planetary descriptions may result from exceptional observational capabilities combined with systematic recording practices maintained across many generations. His analysis suggests that ancient astronomers possessed superior eyesight compared to modern populations, benefited from minimal light pollution, and employed group observation techniques that enhanced their ability to detect faint celestial objects. The theory of enhanced ancient observational abilities finds support in anthropological studies of indigenous peoples who retain traditional skywatching practices. Australian Aboriginal astronomers can distinguish stellar positions and planetary movements that require binoculars for typical modern observers to detect. Similarly, Polynesian navigators demonstrate ability to detect celestial phenomena invisible to untrained observers, suggesting that systematic training and cultural emphasis on astronomical observation can develop human visual capabilities beyond normal ranges. Professor Bradley Schaefer of Louisiana State University has investigated whether optimal atmospheric conditions in ancient Mesopotamia might have enabled naked-eye observation of planets like Uranus and Neptune. His atmospheric modeling indicates that exceptionally clear skies, combined with high-altitude observation sites and ideal viewing geometries, could theoretically allow detection of these distant worlds by observers with exceptional visual acuity and extensive training in stellar observation techniques. However, computer modeling of ancient sky conditions reveals significant limitations to this explanation. Even under optimal atmospheric circumstances, Uranus and Neptune remain at the absolute threshold of human visual detection, requiring observers to know precisely where to look and maintaining observation for extended periods to distinguish planetary motion from stellar background. The level of detail contained in Sumerian descriptions exceeds what could reasonably be obtained through such marginal visual detection. An alternative explanation proposes that ancient astronomers possessed simple optical aids or technological instruments that enhanced their observational capabilities without leaving archaeological traces. Dr. Giovanni Pettinato of the University of Rome has suggested that ancient civilizations may have developed primitive telescopic devices using naturally occurring crystals, water-filled containers, or polished metal surfaces that provided modest magnification for celestial observation. Archaeological evidence for ancient optical technology remains limited but includes discoveries of precisely ground crystal lenses, polished metal mirrors, and glass objects with optical properties that could theoretically enhance visual observation. The famous Nimrod lens, discovered in the ruins of ancient Nineveh and dating to approximately 750 BC, demonstrates optical quality sufficient for modest magnification of distant objects, though its intended use remains disputed among archaeologists. Recent experimental archaeology projects have attempted to reconstruct ancient observational techniques using materials and methods available to Bronze Age civilizations. Dr. Clive Ruggles of Leicester University has demonstrated that systematic observation programs employing multiple observers, standardized recording techniques, and long-term data collection could theoretically achieve precision levels approaching those documented in Sumerian astronomical texts. These experimental studies reveal that ancient astronomers could have developed sophisticated observational methodologies without advanced technology by employing systematic approaches to data collection, statistical analysis of multiple observations, and mathematical techniques for extracting accurate information from noisy observational data. Such approaches would require institutional support and cultural continuity across multiple generations. The cultural transmission theory suggests that Sumerian astronomical knowledge originated from contact with more advanced civilizations that possess superior technological capabilities or observational techniques. This explanation proposes that knowledge was transferred through trade relationships, cultural exchange, or conquest by technologically sophisticated peoples whose own historical records haven't survived or haven't been discovered. Professor Giorgio di Santillano of MIT and Hertha von Dechend of Johann Wolfgang Goethe University developed the theory that ancient astronomical knowledge represents preservation of extremely old scientific traditions dating to prehistoric civilizations with capabilities that exceeded those of their historical successors. Their analysis of mythological and astronomical texts from multiple cultures reveals common themes and technical details that suggest shared origins in much older knowledge systems. The lost civilization hypothesis proposes that human technological development followed a nonlinear path, with advanced civilizations rising and disappearing before the historical periods documented in conventional archaeology. This theory suggests that Sumerian astronomy preserves fragments of knowledge from earlier civilizations that possess superior scientific understanding before experiencing cultural collapse or environmental catastrophe. Recent archaeological discoveries that push back the dates of human technological achievement provide some support for this perspective. Sites like Göbekli Tepe demonstrate sophisticated engineering and astronomical knowledge thousands of years earlier than conventional timelines suggest was possible. These findings indicate that human civilizations may have achieved advanced capabilities much earlier than previously recognized. The extraterrestrial contact theory, popularized by researchers like Zechariah Sitchin, proposes that ancient astronomical knowledge resulted from information transfer from technologically advanced non-human intelligences. This explanation suggests that accurate planetary descriptions were provided by visitors from other worlds who possess space-based observation capabilities and shared their knowledge with human civilizations. While this theory remains highly controversial within mainstream academia, it addresses several puzzling aspects of ancient astronomical knowledge that conventional explanations struggle to account for. The precision of planetary descriptions, the sophisticated mathematical techniques employed, and the technological implications of accurate long-range observation remain difficult to explain through known ancient capabilities. Dr. Michael Kreml, a researcher in alternative archaeology, argues that the conventional timeline of human technological development may be fundamentally flawed, with evidence of advanced knowledge and capabilities appearing much earlier in human history than mainstream theories predict. His analysis suggests that humans may have achieved sophisticated scientific understanding through independent development paths that aren't preserved in conventional archaeological records. The independent development theory proposes that multiple human civilizations developed advanced scientific knowledge through different methodological approaches that achieved similar results without cultural contact or technology transfer. This explanation suggests that sophisticated astronomical knowledge represents a natural outcome of systematic observation and mathematical analysis that humans are capable of achieving given sufficient time and institutional support. Recent discoveries in the history of science reveal that advanced mathematical and observational techniques were developed independently by different cultures at various times throughout human history. The parallel development of sophisticated astronomical knowledge in ancient China, India, and Mesoamerica suggests that humans possess inherent capabilities for developing precise scientific understanding through systematic investigation and mathematical analysis. Contemporary research in cognitive archaeology and the evolution of human intelligence suggests that modern humans possess intellectual capabilities that have remained essentially unchanged for tens of thousands of years. This perspective implies that ancient humans possessed the same fundamental cognitive abilities as contemporary scientists and could theoretically have developed sophisticated scientific knowledge given appropriate cultural support and institutional frameworks. The preservation and transmission of such knowledge across millennia would require sophisticated cultural mechanisms for maintaining accuracy and preventing degradation of complex information. Over time, archaeological evidence suggests that ancient civilizations possessed formal, educational systems, standardized recording practices, and institutional structures capable of supporting long-term preservation of detailed scientific knowledge. Ultimately, the question of how ancient civilizations acquired sophisticated astronomical knowledge remains unresolved, with multiple theories offering partial explanations for different aspects of the evidence. The precision and consistency of Sumerian planetary descriptions continue to challenge conventional understanding of ancient capabilities and suggest possibilities for knowledge acquisition that require further investigation and analysis. Hidden connections. The implications of accurate ancient astronomical knowledge extend far beyond simple historical curiosity to encompass fundamental questions about the nature of human consciousness, the development of scientific understanding, and our species' relationship with the cosmic environment. Recent research in archaeoastronomy, consciousness studies, and comparative mythology reveals patterns that suggest ancient knowledge systems operated according to principles that modern science is only beginning to understand. Dr. Stanislav Grof, a pioneering researcher in consciousness studies and transpersonal psychology, has documented numerous cases of individuals accessing detailed information about astronomical and cosmological phenomena through non-ordinary states of consciousness. His research suggests that human consciousness may possess inherent capabilities for perceiving cosmic relationships and astronomical information through direct intuitive processes rather than conventional sensory observation. The convergence of ancient astronomical accuracy with modern discoveries about consciousness and perception raises profound questions about the mechanisms through which early civilizations acquired their sophisticated knowledge. Traditional materialist explanations that rely solely on technological observation methods struggle to account for the precision and scope of ancient astronomical understanding, suggesting that alternative knowledge acquisition processes may have been involved. Recent research in quantum consciousness theory, developed by physicists like Roger Penrose and Stuart Hameroff, proposes that human consciousness operates according to quantum mechanical principles that enable direct information processing and pattern recognition capabilities beyond conventional cognitive models. These theories suggest that consciousness may possess inherent abilities for perceiving cosmic relationships and astronomical phenomena through non-local quantum information processes. The field of morphic resonance, pioneered by biologist Rupert Sheldrake, proposes that information patterns and knowledge structures can be transmitted across time and space through field effects that operate beyond conventional physical mechanisms. This theoretical framework suggests that astronomical knowledge developed by ancient civilizations could potentially influence the knowledge acquisition processes of later cultures through morphogenetic field interactions. Archaeological evidence reveals that ancient civilizations consistently integrated astronomical knowledge with spiritual practices, consciousness exploration techniques, and systematic methods for accessing non-ordinary states of awareness. Sumerian religious texts describe practices involving meditation, ritual consciousness alteration, and systematic techniques for traveling among the stars that may represent sophisticated methods for acquiring astronomical information through direct consciousness exploration. The ubiquity of accurate astronomical knowledge among ancient cultures worldwide suggests that sophisticated cosmic understanding may represent a fundamental human capability that emerges naturally under appropriate cultural conditions. The independent development of precise astronomical knowledge in ancient Egypt, China, India, Mesoamerica, and other civilizations indicates that such understanding may reflect inherent human abilities rather than isolated technological achievements.